Okay, so as you may have noticed from the introduction, my topic, my focus of research is biological and soft matter samples. So I'm going to be talking about quasi-elastic neutron scattering and giving a few examples of how it has been used in recent years on our instruments for biological and soft matter experiments. The structure of this talk is going to be that I will begin by talking about the ISIS neutron and muon source, just what it is, what we do. I'm going to briefly introduce neutron spectroscopy and then introduce quasi-elastic neutron scattering as a technique. I'm going to be talking about the applications of quasi-elastic neutron scattering for biological and soft matter samples. And after that, I'm going to provide you with a brief summary of the talk, of what we talked about. Sorry. The ISIS neutron and muon source is at the STFC laboratories at the Rutherford Appleton laboratory site. It's at Harvard campus, which is in Didcot, which is in Oxfordshire, the first word that might be more familiar to those who have not already traveled to visit us in the United Kingdom. Over here, you can see that there's also the setup of the diamond light source, from whom I think a speaker will be talking to you after me. We've got a central laser facility. And here you can see the setup of target station 1 and 2 instruments. So the thing that must be most interesting to you is not where we are, but how do you actually go about getting a beam time for your own experiments? To start with, you look at whatever instrument suits you and decide what instrument best works for you. You can see we've got a slight selection on target station 1 and target station 2. And depending on what instrument you choose, I think is the most appropriate, please talk to the instrument scientist. There will be a list on the instrument website of the instrument scientists. Contact anyone or contact the one whom you worked with previously. Talk to them about what you plan to do, what you plan to propose. They will give you input. It will help with your proposal later on. Then, if you're both satisfied with the idea of your experiment, put in a proposal. The next deadline for both target stations is at 5 p.m. British Standard Time on Wednesday, the 20th April 2022. Please feel free to put in a proposal. It should give you enough time from now to prepare easily. So the introduction to neutron spectroscopy. Now let's start with, I'm going to be talking about quasi-elastic neutron scattering. Okay, fair enough. And there's two questions we need to answer before we talk about it. One is, what is neutron spectroscopy? And two, what does this quasi-elastic mean? It's a weird word. You don't come across it that often outside of neutron scattering. But first, neutron spectroscopy. And a good place to start as any is to get nowadays a basic definition of what you're doing from Wikipedia to then start out a more in-depth literature research. So what does Wikipedia say that neutron spectroscopy is? Wikipedia says spectroscopy is the study of the interaction between matter and electromagnetic radiation as a function of the wavelengths or frequency of the radiation. At least that was what Wikipedia said when I prepared these slides. The interesting thing here is to talk about it is between matter and electromagnetic radiation, and again, radiation. Now for neutron scattering, yes, our sample is going to be matter, so that's completely fine. But we're not going to use electromagnetic radiation to scatter from the sample and to probe it. So in case of electromagnetic radiation for neutron spectroscopy, we might prefer to put the terms scattered waves or scattered particles as a function of the wavelengths or frequency of these waves or particles. Obviously, our neutrons are small particles that are accelerated, so the wave-particle dualism does apply to them. So what is neutron spectroscopy? We have an energy transfer after our scattering process, and this gives the information for different and we get this information for different scattering angles. We've got an instrument resolution on any instrument, so our experimental scattering function has to be considered a convolution of the theoretical scattering function from our sample with the resolution of the instrument. And we quite often use time-of-flight spectrometers, since we are pulsed source, as Stuart may have told you, Dr. Stuart Parker may have told you about yesterday. So what we're seeing in a direct source is, there are two ways neutron spectrometers can be, in a very simplified way, be set up. A direct source, which would be a direct, just neutrons going to the sample, being scattered, being detected. Or an indirect source, where the neutrons again go to the sample, then they go to an analyzer from which they scatter and are detected. Talk a bit more about the setups. For the direct setup, what we have is a monochromatic beam where we know the incidence of energy of band of the incident electrons going to the sample and being scattered from it. They will then change the energy at which they're scattered, and by knowing that, and we're using a pulse beam, and by knowing the time of flight that the sample, by detecting the time the neutron takes from the sample to the detector and knowing its distance, we can determine the change in energy. And our resolution really depends on how well we know the sample detector distance and how accurately we can resolve the final time. For an indirect setup, we set in a dispersive neutron beam, so we get a higher intensity of a known energy band, which then scatters from the sample to an analyzer from which only a set fixed final energy is going to be deflected back to a detector. And by knowing how long, by again measuring how long this neutron takes from the sample over the analyzer to the detector and knowing the path lengths, we can then calculate back how long it took to get here. We know what energy it had, so we can calculate back what incident time, what time it took for this path, what energy it must have had there, and thus determine how the energy was changed. So what information do we get out of it? Information about the samples that we can get is diffusion, or rotation. We can get information about phonons and magnons, vibrations, or zero-point energies in neutron scattering in general. You can see here, it's a long range if we go for the intensity plotted versus the transferred energy that you can get. And all of this is available at the EISF sites. Just check out the molecular spectroscopy group. What we are focusing on today is quasi-elastic neutron scattering here, which gives you information about loads of different kinds of diffusion within your sample and is centered around an energy transfer of zero. So why use neutron scattering or neutron spectroscopy? Well, neutrons are neutral particles, which means that they penetrate deeply into matter since they do not interact with the outer electron shells of the particle of your sample, but instead with the nuclei being neutrally charged. So they may penetrate quite deeply before the first scattering event takes place. And compared to X-ray scattering, they tend to be less destructive, although it also quite often can take a bit longer to get the same results. They have a spin of 1/2, which means that they do interact with the spins of your sample. They can detect magnetic moments and magnetic structures, and so they have a magnetic moment, meaning they can detect magnetic structures and excitations within your sample. Additionally, their wavelengths is similar to atomic spacing, depending on the energy range resolution chosen, and can be in the picometer to micrometer range. They interact with nuclei, as specifically said previously, which means that they are sensitive to light, and they are sensitive to light atoms such as hydrogen, as you can see here from the scattering cross-section, compared to X-ray scattering, which goes with the scales with the atomic number, and therefore is not as sensitive to light atoms and more sensitive to large heavy atoms. Also, neutron scattering can differentiate, as you can see here, in the scattering cross-section it sees between different isotopes, which can be quite useful if you want to determine how isotopes are arranged. And it is possible to use the change in different scattering cross-sections between the different isotopes to do something called contrast variation, where you adjust the isotopic content of your sample in order to reduce the scattering cross-section of one part of your sample that you need for functionality, but are not interested in looking at in analyzing, so would like to not contribute to your scattering result, by making sure that the scattering cross-section matches that of your environment and goes to zero in the sum. So now that we've talked about neutron spectroscopy and why neutron scattering in general is good, let's go talk about what quasi-elastic neutron scattering is and why it is a very good method that I think is very well suited to loads of questions. So quasi-elastic neutron scattering gives us the acronym QENS or QENS. What is quasi-elastic scattering? So what does the word quasi-elastic mean? Neutron scattering, neutron spectroscopy, we talked about this. It's easy, it's understood now, and it's clear. Let's just briefly repeat what elastic scattering is. We've got an incident wave vector at a known initial energy that is scattered, and we get a final wave vector at a final energy. There is no change in energy, so the energy transfer is 0, and the absolute value of the wave vectors is identical and can be described as 2 pi divided by lambda. We get a Q value that we can calculate. That's it. Now, what is inelastic scattering? Since quasi-elastic means we're not going to be only elastic. Now, we've got an incident wave vector and an initial energy again that is going to be scattered with the final wave vector that has a different absolute value to the incident one, and the final energy is going to be different. So we've got an energy transfer, Ki unequal Kf, and the energy transfer, delta E or h bar omega, can be described as the initial energy, and from that we subtract the final energy. There you get your equations. So for this quasi-elastic, if we use these elastic and inelastic equations, we get that quasi-elastic scattering has a change in the initial and the final wave vector. There is an energy transfer as in the inelastic, but like in the elastic scattering, it is centered around 0 and it is very small. So if you can imagine that here we have the instrument resolution experimentally determined in blue. What you get for the quasi-elastic part is a broadening of the peak. This elastic peak just gets broader if you're going quasi-elastic. And this broadening is caused by the dynamics in the sample. Due to the sample having, due to the atoms and nuclei within the sample or the molecules being mobile and having dynamics, when a scattering event takes place, what would be an elastic event at 0 Kelvin when nothing were mobile, where the samples were, if the sample was completely immobilized, suddenly becomes quasi-elastic due to the motion of the nucleus from which we are scattering, causing a transfer in energy between the nucleus and the neutron. That's where quasi-elastic is coming from. So quasi-elastic neutron scattering designates a limit in case of inelastic neutron scattering as characterized by energy transfers being small compared to the incident energy of the scattered particles. The energy and time scale are relevant and related. If you know the energy resolution of any instrument you choose, or where it can be set up, you can use it to calculate tau, the time which you're going to be observing anything on. By using this equation, you can just use tau equals h divided by the energy resolution. And thus you can select the time scale on which you expect the dynamics you're interested in to take place. Usually you can resolve between 10 nanoseconds and 1 picosecond on quasi-elastic on the Quenz instruments, although slower timescales can be observed using the spin echo, which I'm not going to talk about now. And they are millielectron volt to 0.1 microelectron volt energy resolutions. The momentum and distance that you observe, 0.1 angstrom to the power of -1 to 5 angstrom to the power of -1, and 1 angstrom to 16 angstroms, correspond well with most distances that you see. The distance you're probing is, of course, related to the Q value you're looking at. You can see here how quasi-elastic neutron scattering in the middle, as I'm circling it, it's around on the energy range of Brillouin motions. Raman photon correlations are higher and lower respectively. And you can see that time-wise, the time scales are comparable to some other techniques and the energy range. So you can see how it compares to other methods and see what for your question is the most appropriate. Usually what we can look at easily is hydrogen diffusion in polymers and glasses, backscattering or time of flight techniques. We can look at confinement in biological samples, molecular reorientation, tornado and nuclear spin excitations. So again, what are we observing? Here's an example of a spectrum taken where you can see the scattering functions intensity plotted against the energy change. And what we're seeing is that we get the scattering function consisting of the incoherent and coherent scattering contribution, which is related to something called the double differential scattering cross-section, linearly related to the scattering cross-section, the scattering function. So our incoherent scattering cross-section, which is the one that we mainly get due to coherence events being possible, but rarely done, since the main questions asked are going to be answered by incoherent scattering due to the presence of hydrogen. So what you get is usually you use one delta, use a 4 factor that we're going to be talking about in a bit more detail later, and a delta function plus 1 over pi multiplied with the sum of a 4 factor of different Lorentzians, as many as you need. In this case, 2 Lorentzians was 2 separate functions, each with 1 Lorentzian was chosen and convoluted, so that you have 2 Lorentzians describing the dynamics taking place, 1 each for the dynamics you're able to see on the timescale chosen, describing the complete scattering cross-section. You see a scattering function. Incoherent scattering gives you no structural information, which is the case for all of quasi-elastic Neutron scattering, although due to knowing on which time scale an experiment takes place and having previously characterized your sample, you will of course be able to make assumptions and educated guesses about what dynamics take place where. You also get information about individual particles, whereas coherent scattering shows you the correlation between nuclei, and it also broadens the elastic peak due to the structure and collective dynamics of the nuclei that take place. If you're looking here, you can see the scattering cross sections, usually coherent and incoherent, both take part in the scattering cross sections. You can see that hydrogen is one of the strongest incoherent scatterers by far. So the moment you have hydrogen present, you're going to be seeing the hydrogen, and you're going to be doing incoherent events. What you can do is you can replace it with deuterium. And if you look, I apologize, there's a space mission. This is the incoherent scattering cross section. And if you replace hydrogen with deuterium by deuterating a sample, talk to any deuteration lab, or if you have just solvent that's H2O based, change it to D2O and you should be fine. You can hide some of the hydrogens you're not interested in seeing. So what is the scattering cross section? It is linearly related to the scattered intensity by having to be multiplied with the incident scattering intensity. The unit of the scattering cross section is barn, which is equal to 10 to the power of minus 28 meters squared. It is related to the incident wavelengths or velocity of the neutron. And here you can see with all these nice integrals what it is mathematically defined as, which amounts to we have a sample from which something is scattering into an area delta d omega defined here. We see the change in how many particles we get scattered through. For the double differential scattering cross section, we're then also interested in how the energy of the scattered particles changes. So what do we observe by grants? I've now shown a scale which gives you the different time scales for biological samples, as this is my main focus. You can see is the diffusion of particles in solution or domain vibrations, side chain fluctuations, conformational transitions. We're tracking all this information by looking at the broadening of the peak, something called the elastic incoherent structure factor and mean square displacement, which I'll be talking about a bit more later as we come across them. So here you can see how the time scale is really relevant for what you're seeing and can be chosen appropriately to what you're trying to track. If you're interested in domain vibration or H-bond vibrations, which you can get in any sample that has H-bonds, you should go to the 0.1 to 1 picosecond time scale. Well, if you're interested in how the H-bonds break, rotational relaxation or translational diffusion, the 1 to 10 picosecond time scale to look at these H-bonds would be more appropriate. If you're interested in collective water dipole relaxation, 10 to 100 picoseconds are the time scale to look at, while side chain fluctuations in a protein, so if you imagine any protein has loads of different residues and chains and some of these fluctuate, you should go to the 1 to 10 nanosecond time scale. If the whole protein is tumbling around in any solvent or environment where it can move freely, this would be 10 to 100 nanoseconds. And if a protein changes its arrangements, it's how it is arranged, for instance, if it had been disordered and now has to go back into a working structure and is capable of doing so, we would be talking about conformational transitions on the microsecond time scale. So again, what do we see? Quasi-elastic inelastic neutron scattering, which is basically what we, and incoherent neutron scattering. I'm sorry, I should say incoherent. Incoherent neutron scattering is what we're basically going to be talking about. All of these can also be done for coherent scatterers, but please double check that any equation mentioned here has also theoretically been proven for coherent scatterers. We'll be looking at is the change in energy, diffusion at molecular scale. We'll be able to differentiate diffusion and confined dynamics for our samples if they happen at the same time scale. And the time and length scales, which is where we need, are comparable to that available in molecular dynamics simulations. So any assumptions you make about your sample experimentally can also be verified or compared to a simulation, and contrasts can be adjusted and matched if and when required. So let's talk about the applications of quasi-elastic neutron scattering for biological and soft matter samples. So what are we measuring? A non-exhaustive list of potential biological and soft matter samples are proteins or molecules in solution, looking at the behavior in cell, looking at the behavior of cell membranes, lipids, molecules, tissue samples, protein powders, a lot more. Could also be looking at polymers, nanoparticles, and of course, any condensed matter sample that has dynamics on the relevant timescale. How are we going to do this? This is a shorter list. We're going to look at the global diffusive behavior if it is in the time window. We're going to look at internal diffusive behavior. We're going to look at the flexibility of the sample using the incoherent structure factor. And we're going to do something called temperature-based Kelvin or elastic window scans to check for transitions in the sample. So how are we measuring it? For direct scattering, just as a brief reminder, we can either use, for Quants, you can either use the direct scattering as you would find at the LET on ISIS at target station 2, or you can use indirect scattering as you would find for IRIS or OSIRIS at target station 1, which is just how the instruments are set up. The result you would get is a Q dependent on the detector's position. You know it is Q dependent, either for a continuous bank where you're binning it as you choose, or where each detector is aligned to a set Q value. And there you would be getting the intensity at different energies. So an example, or I've chosen 4 examples of samples that have recently been analyzed just to show you that while we're looking at the same parameters for each experiment, we do get different information from it, and the versatility of the method can be well explained by these. So if we looked at streptavidin and biotin, which would be a protein interacting with the ligand, something binding to it, a vitamin in this case, that's looking at a protein in solution. Healthy and tumor cells have been investigated using Quants. There the intracellular water was of interest. For caffeine interacting with the DODAP, so lipid membrane, the molecule and lipid in different phases were analyzed, and this was very interesting because caffeine is, of course, something that we all know and use and are familiar with, but can also be used to support the effect of anti-inflammatory pain medication. And it is important in order to use this more efficiently and understand it better, to understand the interaction effect of caffeine with lipids. So DODAP membrane was chosen for this case. And what's also found is looked at was a set of bacteria called Shivanella onedensis under different pressures in order to understand better how pressure resistant strains of these bacteria in a set buffer can be obtained and what changes for these bacteria cultures that become more pressure resistant than those cultures that have not been trained to resist the pressure. So the questions that we asked in corresponding order for the first set of samples was, how do the dynamics and the conformational entropy change upon ligand binding? So I'm not going to go into too much detail about the conformational entropy, but making a few assumptions, you can actually get changes in conformational entropy by comparing two samples using Quants. Next question was, what are the dynamical properties of intracellular water in cancer and non-cancer cells? Also very important to just understand what exactly cancer is changing in a cell in order to improve treatment and understand how and why treatment is effective. Then the question was, how does the caffeine modulate the dynamics of the DODAP lipid membranes? And how do intercellular water dynamics change within this bacteria cells depending on the pressure? And how do we answer all these questions? We actually do the same. We look at the quasi-elastic neutron scattering, broadening, elastic incoherent structure factor, mean square displacement to track dynamics and flexibility. For some of the samples, we're also going to do the elastic fixed window scan, which can also be called EFWS, versus different temperatures to get temperature dependent dynamics and transitions. So how do we get information from the peak broadening? Again, this is our general function. And each peak broadening in the Lorentzian functions, gamma e, corresponds to a different dynamic. If we're using fixed law, we can get information about the global diffusion that is usually modeled by the smallest Lorentzian if it is present. By looking at the whole Worth-Singh, Fisiolander, or jump diffusion equations to describe diffusion and the peak broadening of one of our broader Lorentzians, or only one if we're on very, very small time scales. We can get information about the internal dynamic, which gives us a bit more microscopic understanding by understanding how exactly this diffusion we're seeing is taking place, if it is a jump diffusive behavior, whether it is taking place on a Bravais lattice, whether it is just purely random or slightly ordered and entered. So an example of information we determined from peak broadening. Now, first of all, I'd like to talk about the streptavidin-biotin interaction on the picosecond timescale. What you can see here is that the pure protein was plotted, protein's peak broadening was plotted against Q squared. And it is following the equation best described by the random jump diffusion. But if you added the ligand, you suddenly do not find this jump diffusion anymore. It seems to be centered more around a straight line that was calculated by using the weighted mean of these values with the errors. And while this is showing Q-dependent behavior, here we see Q-independent behavior. Q-independent behavior in any peak broadening indicates that we're seeing localized restricted motions. And now, having seen this, that the behavior is changing on the same time scale, this allows indications which are that the surface residues that are taking place, that would correspond on the picosecond time scale to where the jump diffusion can take place, because only they move fast enough in a protein to be mobile on the picosecond time scale, must become tighter, because if you add, before you add the ligand, you see free flexible motion. And after you add the ligand, you do not see this motion anymore. So you can understand it to mean that the sample has become more restricted and tighter. And this indicates how just looking at two diffusive models two diffusion processes can be used to understand the dynamics of a sample. Another example would be looking at the peak broadening from normal to cancer cell transformations. So there were two Lorentzians fitted, I apologize, 3. And the full width half maximum was plotted against Q squared. So for the hydration water, they were able to find that it was a linear behavior following Fick's law. And this could be found that there was a difference between prostate and cancer cells and healthy prostate cells. The same was the case for the cytoplasmic water and just for the water in general. And what they were able to find by fitting both a random jump diffusion model as well as a global linear diffusion model was that the cytoplasmic water, checked here, is more flexible than the hydration water around. So there was a greater flexibility. And also that the cytomatrix, so the surrounding anyway, is more flexible in malignant cells due to the DQT increase. So just this increased flexibility, malignant cells compared to healthy cells, is a good step to understanding what makes the difference and how cancer cells form, what's to be watched out for, and also what needs to be suppressed in any treatment. Because of obviously finding any difference between healthy and cancerous cells increases the chance of finding a way to only target that difference and not target something that some properties that both cells share. You don't want to kill the healthy cells tissue around it. What was also used there is that if we think back to our Lorentzian function, our scattering functions, we see that there's a 4 factor giving the peak area. relevant for each broadening effect. And by looking at how this ratio changes for the same parameter observed between different tissues, you can also get information. This area changes. You can see there's a continuous trend in this case for the healthy to have a higher area, to have a larger contribution of the global dynamics, while the non-healthy cells seem to be slightly less contributing there, but more contributing to in the localized dynamics. So you can also see how not only the dynamic behavior changes, but the influence on the total dynamics of different dynamic behaviors is also changing, and you can track that using this 4-factor. Another information of peak broadening was gotten by fitting the curves of the DODAP and caffeine DODAP membranes with and without the caffeine membranes. Lateral dynamics are again a linear relationship diffusion used in Fick's law. And another thing was this one here, where you find a more complex diffusive behavior when an appropriate model was again chosen, as you can see. And this showed that the dynamics of DODAP are altered by added caffeine. You can see quite nicely that the curves do not overlap. And this was done for the corrigal phase, which is a sort of semi-crystalline fixed gel phase that comes after the gel phase. And you can find that coffeine has enhanced any dynamics that are present, while in the lipid phase, not shown here, the lipid dynamics have been restricted. Another example, as I mentioned previously, would be the pressure-resistant bacteria Chivanella onadensis, where the water diffusion dt was measured. So let's go here. For this, using a jump diffusion coefficient, there was also, and the rotational relaxation was calculated from looking at how this internal peak broadening is going, just the rotational relaxation that's there locally. And what could be found by comparing the diffusion coefficient, translational diffusion coefficients determined, is that channel for the free type, the wild type, and the pressure resistant type at different pressures, each measured at different pressures. Here, the pressure given is the pressure for which the bacteria were trained. So what could be found was that there are channels within the bacteria through which the intracellular water moves. They become constricted more, and there's more constriction of these channels present, meaning that the directions into which the intercellular water can move have been restricted more for bacteria that are more pressure resistant, and the internal viscosity of this liquid medium, this tessolic medium within this bacteria is found to be increased if the bacteria are pressure resistant. So it seems to be that they form structures and guide the water within them more if they become pressure resistant, in order to avoid the water going waste they wouldn't like it to do and the pressure causing them to burst. So the results we could obtain just from looking at the peak broadening, well, we can use it to analyze diffusion. And this gives us information about the internal dynamics, the internal structure, intracellular water behavior, global dynamical change, global structural change, even if we extrapolate how the dynamical change can be caused by structure. And of course, several other aspects depending on what different samples we would use. Now, we also have the elastic incoherent structure factor I previously mentioned, which is this 4-factor, the first one we saw, A0 of Q or EISF. And what it gives us is information about the fraction of elastic contribution. So what we do get is the we use is the incoherent elastic part of the incoherent scattering function, and we divide it by the sum of the elastic part of the incoherent scattering function plus the sum of the quasi-elastic part of the incoherent scattering function. So really the whole incoherent scattering function that we do get. And this can be used to describe the local restricted motions of a single particle. At least that's what the theoretical equations are for. However, obviously, no sample will consist of just a single particle. So what we're getting experimentally is the average over all the single particles that are described by the equations within our sample. And there can be different models used. Again, a non-exhaustive list, just what I'm going to be briefly touching upon. There can be models used to describe jumps between 2 or 3 or n sites. there can be models used to describe diffusion on a sphere, or in a very simple case, we can just use the Gaussian approximation if we're not quite sure what model we have. And if we were to transform it into the appropriate space, you would find a Gaussian shape. So first of all, the elastic incoherence structure factor, we should consider what is the difference between long range versus localized diffusion. For a long range diffusion, our peak broadening delta omega or gamma is modeled and Q dependent, as you could see here in black. While for localized diffusion, delta omega of Q is Q independent and is not being modeled. And long range diffusion, the elastic incoherence structure factor AO of Q is Q independent. While if we have localized diffusion, AO of Q can be modeled and is Q dependent. Experimentally speaking, you usually always have some sort of localized diffusion taking place. So even if your diffusive behavior seems to be Q independent, it's always worth it to just get your elastic incoherence structure factor and plot it against Q to double check that there's no slight dynamics you might wish to model. You're getting it from fitting your spectra anyway. So the different models for the elastic incoherence structure factor. The easiest one would be the jump between two equivalent sides, where on a circle you would have side 1 and side 2, and your particle could just be on either side jumping between them. And there the elastic incoherence structure factor would be described as AO of Q equals 1/2 multiplied with 1 plus the 0th order Bessel function of QD, D being the distance between the sides in this case being identical to the diameter, but obviously that would not be the case if we add additional sides. And you use a Fourier transformation of the intermediate scattering function, which you get first, to arrive at AO of Q delta omega plus A1 of Q 1 divided by pi 2 tau divided by 4 plus omega squared 2 squared. Can see here an example of how the elastic incoherence structure factor would look extended to Q equals 10 for two equivalent sides. Experimentally speaking, again, you rarely ever go up to these high Qs. If we now say we extrapolate it to n equivalent sides, we get this equation, which contains the average probability that any side I is occupied. So if you have n sides, this probability, if the sides are equivalent, would be 1 divided by n. Then you get the influence of the dynamical probability of a jump taking place from side I to side j, which would be described by this nice factor, and the spatial correlation. This intermediate incoherent scattering function you would then Fourier transform from the time into the energy space and get, again, the elastic incoherent structure factor and the elastic contribution, plus a sum of Lorentzians, which are now a bit more involved to calculate. The four factors are now a bit more complicated. There you go. If you now plot it for a different amount of sides, you can see here going to about QR equals 3 for 2 sides that we saw previously, just cut off a bit more. If you add another side for 3 sides, you see this. If you're going for 4 sides, you can see that the relative change between 3 and 4 sides is less than between 2 and 3 sides. 4 and 5 sides, again, is smaller, and 5 and 6, the change is hardly visible. So from what you can reasonably resolve and fit and analyze to separate, you don't tend to go higher than at a maximum 7 equivalent sides. Quite often you go less, no more than 3 or 4. If you feel like you need more than n equivalent sides, it might be more appropriate to choose a model that describes a continuous motion on a circle, simply because it is not possible to resolve more than about 7 equivalent sides. Of course, any system is different, and there might be special cases where the number can be higher. So we can also have diffusion in a sphere that is suitable to describe any molecules behind in a cavity or in a cell or similar, but also just any motion that you're sure takes place within a spherical volume. And what's important here is that something called the self-correlation function at infinite time can never be 0. There must always be a particle. This behavior is similar to localized diffusion, and the information that you get is about the shape and the structure of the sphere that's contained over this radius A. So if you see the elastic incoherent structure factor here is 3 times the first order Bessel function of Q times A being the radius of the sphere divided by Q times A, and that's squared. So if you were to plot that against Q, you would get information about the radius of the sphere your particle is moving in, or since you have multiple particles, the average radius of any sphere of the spheres in which these motions take place. Now, a very simple model is the Gaussian approximation, which is applicable for systems with diffusion following simple diffusion equations, follow Langevins equation, or if the Van Hoff self-correlation function has a Gaussian shape in space. In this case, your elastic incoherent structure factor can be described as e to the power of minus u squared q squared, where u squared is your mean square displacement. That's something like the mean square area in which your particle is moving about, multiplied with 1 minus p plus p. P in this case being a factor that can be 0 but doesn't have to be. It just describes any section that seems to be immobile, that doesn't seem to be moving around. This can easily happen if, let's say, a part of your dynamics takes place on the nanosecond time scale and you're getting the elastic incoherent structure factor on the picosecond time scale. Now, any motions that are significantly slower than your chosen time scale will, of course, not be resolved and appear as immobile parts. So that's where P comes in. And then we have this mean square displacement, which describes the behavior over time is related to diffusive motion. It's a model-free way of modeling structural changes, dynamical changes in your protein. It's limiting case, again, mathematical stuff. And if you're looking at this model-free way, what you can do very easily is just you see that the mean square area that's available to your protein or your polymer or to any part of the sample is reduced, the dynamics must be reduced. You don't quite know what it is. You don't even know, maybe not confidently know enough to choose an appropriate model to say, that's definitely a jump between 3 sites. Maybe you don't know how many sites there are, even if it is jump motion or continuous diffusive motion. In this case, just looking at the mean square displacement, you can get loads of information. You can also use it to get information about the force constant in the protein. Although in that case, you need to use 2 times, in this case, the force constant is 2 times multiplied with the Boltzmann constant divided by the change in mean square displacement depending on the temperature. And for that, to get the mean square displacement temperature dependently, what you use is this scattering function at energy change 0. And how it changes? Because the elastic factor or the elastic part of your sample, the elastic contribution that you get for any scattering is reduced and goes down if you're increasing in dynamics, because elastic scattering comes from seemingly immobile parts where no motion is taking place. So if you get increased dynamics, you get less elastic scattering because any dynamics in your sample will cause quasi-elastic scattering to occur. So this is the elastic fixed window scan. It uses the intensity of the elastic scan or the elastic part of your peak. It is usually measured for a change in temperature, since temperature changes bring about transitions, and transitions are correlated to changes in dynamics. It can be used to show phase transitions. And you can also use it to determine the mean square displacement if a Gaussian shape is present in the reciprocal space, using the equation printed up here or easily fitted, a constant multiplied with e times minus u squared q squared. So you can just take the logarithm of the scattering function, plot it against q squared, and get the slope. So examples of experiments that we used performed and information that was obtained using both the elastic incoherent structure factor and either or elastic scans as well. For streptavidin and biotin, the information found was a difference in flexibility and a change in the flexible sections. For the healthy and tumor cells, it was found that bone cancer tumor cells are less flexible than other tumors, which may sound intuitive, but had to be proven and checked. And it is good to know that the cellular behavior is different for cells tumor cells that show a drastically different behavior. Caffeine and DODAP membranes found that caffeine does not shift the phase transition, but the radius of motion does, I'm sorry, the nut shouldn't be here, change over the elastic incoherent structure factor. The pressure-resistant trained bacteria, Chivanella oneidensis under pressure, used models with various radii to fit it. They found that the fraction of the mobile section changes, so the parts that are actually mobile on the chosen timescale change if the bacteria, depending on whether or not the bacteria were trained to be pressure-resistant. And an extra structural contribution seems to be causing this pressure resistance, so the cells must have built some sort of something around them or gotten more stable. And we're now talking about examples of information determined by the elastic incoherent structure factor for the streptavidin and biotin. You can nicely see that here on the nanosecond time scale, the mean square displacement is reducing by adding biotin, but all parts seem to be mobile. So there are no motions taking place on significant slower timescales than the nanosecond timescale. On the picosecond timescale, all those motions that were on the nanosecond timescale are now no longer resolved. So we can see here, this was modeled using the Gaussian approximation. A p factor does increase. You still see that the flexibility of the streptavidin plus biotin complex is reduced compared to the pure streptavidin, but you no longer see, but you don't no longer see it going to zero. Instead, you see that there's an immobile section that actually increases upon ligand addition. So what this found was a difference in flexibility and a change in which sections are part of the protein are flexible. Since there's a difference in the factor that is seemingly mobile, there must be a change there. So examples of information we could get from the elastic scans. Looking at the healthy and tumor cells, you can here see an elastic temperature dependent scan that has been performed just by plotting the sum over all Q of the elastic part with the temperature. And what you can see here is that right now it is fairly stable in a structure and fairly non-flexible. And as the melting temperature is reached, you can see that the flexibility does increase. So the elastic section drastically drops down. You can also see is that the mean square displacement as a Q-dependent behavior was determined using the equation we talked about and plotted against, that the elastic fraction was plotted against Q in order to see its Q-dependent behavior. And you can see that both the amplitude as well as the position where the amplitude change takes place is different for the different samples. So we found that the bone cancer tumor cells are less flexible than other tumors. It was found, sorry. And information gotten from a sample where both the elastic incoherent structure factor and the elastic scan were used was the coffeine and DODAP membrane. Now, the first thing to look at is the hysteresis obtained using the elastic intensity from the coagul to the fluid phase. You can see here, again, the dropping down to a fluid phase, dynamics increasing, elastic section decreasing. Then was cooled again over a gel phase, and black, the pure membrane, and with the added caffeine. We can find is that the phase transition temperature is not shifted, but the addition of caffeine seems to change something. And by looking at the elastic incoherent structure factor, can be found that adding caffeine increases the mean square displacement in both the phases. So this is a good indication that adding caffeine to the membrane increases disorder. Another thing we talked about, I mentioned previously, was the information determined from the elastic incoherent structure factor for the pressure-resistant bacteria. So you can see over here. And in this case, there were models with various radii fitted. So in this case, diffusion in a sphere was assumed, but also if mobile section was included, but the model was adjusted slightly to increase an accounting of the immobile section or mobile sections. So the mobile sections changes and extra structural contributions are most likely the cause were extrapolated to exist due to the change in the mobile sections. Having talked about this, which was quite the sum of different experiments, what was the summary information, the takeaway message? So what we did was we defined what quasi-elastic neutron scattering is. We talked about it being the broadening of an elastic scattering caused by dynamics. From this broadening, we can get the diffusion coefficients by choosing different time scales depending on the energy resolution of the experimental setup. We can observe different processes. By getting different diffusive aspects, we can get information about diffusive microscopic processes within our sample. And we talked about currents being mainly in coherent scattering, although coherent currents can be done if necessary. We talked about the differences between long-range diffusion and localized diffusion, that the peak broadening in long-range diffusion is moderate and Q-dependent, and the elastic incoherent structure factor would be Q-independent. That for localized diffusion, we get a Q-independent peak broadening, but we do get an elastic incoherent structure factor that is Q-dependent, and by modeling it, we do get information. We talked about the elastic incoherent structure factor and the mean square displacement describing the microscopic behavior. Sorry, that should be microscopic, not macroscopic. They allow different models to describe the behavior, and they allow for model-independent descriptions of protein behavior. Last of all, I'd like to acknowledge that the graphics I took and are not solely my own, so I'd like to give the references of where I took them from. A good book always to use to get more information would be the book on quasi-elastic neutron scattering by B. And if you have any additional questions, please feel free to ask them. Thank you for your attention.